Lab report for Physics 2212, lab number 4. Introduction. The purpose of this lab was to use the principles of energy conservation and charge conservation through the loop rule and node rule to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. The physics principles used in this lab were Kirchhoff's loop rule, node rule, and Ohm's law. The loop rule states that delta V equals 0 for round trips in static electric fields due to path independence. And the node rule states that for nodes with currents in steady state, the current going in is the same as the current going out. Ohm's law states that delta V equals IR, where I is current and R is resistance. The models used for this lab were mainly circuit diagrams, examples of which can be shown to the right-hand side. The main result of this lab was that the experimentally determined currents and voltages matched those predicted by the equations. And furthermore, in an RC circuit, the strength of a current was shown to be dependent on time and was modeled with differential equations. So for the simulated experiment, the system was the circuit and the surroundings for everything else. The initial conditions varied between experiments, but all of them used complete closed circuits unless stated otherwise. And the main assumption was that the resistance of wires and ammeters were considered to be negligible. So for the series circuit, I recreated a circuit from the circuit diagram shown in the upper right, and then used ammeters and voltmeters to measure the currents and voltages of different parts of the circuit. I found that I1 equals I2 for the two ammeters in the circuit diagram, and the exact current was found to be 0.02 amps. If connected backward, the ammeter read negative 0.02 amps, and if an ammeter was replaced by a voltmeter, the circuit was open. So therefore, delta V was 3 volts and I was 0 amps. I then measured the potential differences across various different points of the circuit and found that delta V across all wires was 0 volts, for example, from B to C. Delta V, or the potential difference between A and B was 3 volts due to the two batteries in series. The difference between C and D was negative 0.96 volts. The difference between E and F was negative 2.04 volts. The delta V for the round trip was found to be 0 if you add everything up together, and this verifies Kirchhoff's loop rule. I still remain as 0.02 amps, and the ammeter reading does not change since the voltmeter has a very high resistance, causing the circuit to continue acting like a series circuit, despite the voltmeter being inserted in parallel. You can also see in the bottom right-hand corner, I graphed the circuit with the voltages over various parts of the circuit. You can see that the batteries cause the voltages to increase, and the resistors cause the voltages to decrease. So for the next part of the experiment, I connected an ammeter in parallel with the 100 ohm resistor, which causes current to drop since the ammeter has virtually no resistance. And this allowed us to get the measured resistances of each resistor. And these numbers were slightly different from the measured or from the actual 47 ohm and 100 ohm resistors. They found to be 48 and 102 ohms respectively. And the resistance of the wire and ammeter were 0 ohms. In conclusion, the macroscopic circuit analysis equations still hold true, but the difference in calculated and actual resistances can be due to the ammeter's low precision. For the RC circuit, I connected a battery to the RC circuit where the bulb starts bright and then dims until it goes out, and then the current decreases from a maximum to 0 amps. Meanwhile, the charge on the capacitor accumulates, as marked with the plus and minus signs on the plates. When the battery is disconnected and the circuit is closed, the bulb starts bright and then dims until it goes out again. The current once again decreases from its maximum to 0 amps, and the charge on the capacitor drains. For the 10 ohm light bulb, it took 10.5 seconds to charge and 12.4 seconds to discharge. And for the 20 ohm light bulb, it took 17.3 seconds to charge and 22.3 seconds to discharge. So for the RC circuit, you can start off by summing all the potential differences to 0, and then you get the mathematical equations listed to the upper left-hand corner. You can do some math, some simplifying to isolate the equations such that ln of delta V over delta V naught is found to be equal to negative T over RC, RC being the time constant for the circuit. The data shown on the middle and right-hand side is for a 30 ohm light bulb in an RC circuit. And when you put everything together, you can see a linear relationship between time and ln of delta V over V naught, with the slope being 1 over RC. Here in this case, RC is meant to be negative 1 over negative 0.1668, which is approximately 6 seconds, which matches the 30 ohms times 0.02 amps from Ohm's law. In conclusion, the differential relationship between current over time and capacitance over time holds true. So there were some discrepancies. In the series circuit, the resistances calculated from Ohm's law were slightly different from the actual resistances in simulation, and this is likely due to the ammeter's low precision. And a possible source of error, like the timings in the RC circuit, could be off due to human error just starting and stopping the separate timer. And if this law was being done in real life and I used an actual ammeter instead of an ideal simulated ammeter, a real life ammeter would have some slight resistance. The current reading would be slightly lower. And if I were doing this lab in real life and use a battery to charge a real capacitor with no resistor in the circuit, then the ideal model would predict that the capacitor would charge nearly instantaneously without a resistor, as the resistor would be what kind of slows the charging of the capacitor. However, in real life, this process would be slightly slower, but still